Welcome. This is lecture 33. In this we give a proof of Noether normalization lemma, which is the following. Let's recall what Noether normalization lemma was. So theorem. This is Noether normalization lemma. Okay. It says that if R is a finitely generated K algebra, K field, then there exists some finitely many Z1 through Zd inside R, algebraically independent over K, such that R is finite over is a finite algebra. In other words, as a module it is finitely generated. Finite algebra over this subring. Which itself is a polynomial ring because it is algebraically dependent. Okay. So we saw a proof of this last time for algebraically closed fields, for infinite fields, where we did change of coordinates, and the change of coordinates ensured that some element in some relation among the generators of R can be written in a monic polynomial form. Okay. And once a relation among the generators can be written using a monic polynomial, it says that one of the generators is integrally dependent on the other, and hence the morphism is is finite, and then using that we can bring the number of generators down. Okay. So that was what we did last time. So here also the idea is the same, but the proof is a little bit more involved, and we will see an example after this proof that if the field is finite, one cannot really there are situations where one might not be able to find linear change of coordinates like the one that we did last time. Remember, that was just yi went to some yi minus some appropriately chosen constant from k times yn. Okay. So that would not be possible. Okay, so now let's give the proof in the general case. Okay. So it's the same idea. So let's write. Let's say R is k little y through little yn, okay, and think of R as a quotient of the polynomial ring in that many variables y1 through yn. Okay, and if this is an isomorphism, if the kernel is 0, then there is nothing to prove. So all of this is the same approaches from the last time. If the kernel is 0, okay, then there is nothing to prove, because then this itself is a polynomial ring and it is finite over itself. Okay, so that's nothing to prove. So then therefore assume that there exists some polynomial f in the variables y1 through yn in the kernel, non-zero polynomial. Okay. So the idea is again to change coordinates so that f takes the form of a monic polynomial, and that would introduce a relation of little yn over some combination of the earlier ones, not necessarily the earlier y's. Okay. Okay. So now let's so suppose let's write f as some sum of some coefficients alpha A indexed by some n tuple x1, E is just this n tuple E1 through En. Sorry, Y1 through Yn. These are the variables. Okay, f is of this form. Okay, so yeah. So now we do we would like to do a change of coordinates so that this polynomial will take the form of a monic polynomial with coefficients coming from monic polynomial, and the coefficients of lower powers of Yn may come from the earlier variables. Those variables, okay, we'll change them a little bit. So the change of coordinates that we will try to attempt is change of coordinates. Okay, we write yi star as yi minus yn to the ri, okay, where these are positive integers to be decided, positive integers to be determined, and we'll see what we have to determine. Okay. Okay. So then a monomial of the form y1 to the e1, y2 to the e2 up to yn to the en, okay, under this change of coordinates, this is the same as y1 star plus yn to the r1 to the e1 and so on. So there is a change up to this point, yn minus 1 star plus yn to the rn minus 1 to the en minus 1, and then so one more term yn to the en. Okay. So this is the expression that we get. Okay. So this will have a term. So just this monomial itself will have a term which looks like yn to the EIRI plus, so this, for this monomial, this term here would be this monomial will get converted into some polynomial where this coefficient here is 1, and then some lower degree terms in yn, coefficients from the other variables y1 star through yn minus 1 star. Okay. Here the coefficient is from k and it is 1. Okay. So this looks like this. Okay. So now suppose, so recall that f was some coefficient times this one. Okay. And we can assume that ai's are non-zero, otherwise they will not appear in the sum anyway. Okay. So we would like to choose these ri's so that each of these monomials will give a term, and this monic term that we get here with unit coefficient are distinct, so that they will never cancel each other, and therefore f will get transformed to a monic polynomial. Okay. So this is just to ensure that whatever f gets transformed to has leading, if you write it as a polynomial in yn, the leading coefficient is a unit. Okay. So we want to choose ri. So one way to, so we want to ensure that f is transformed into a polynomial, let's say g of y1 star through yn minus 1 star yn, that is monic in yn. Okay, so this is what we want. This the idea is the same from the other proof, but it is just one requires a little bit more work to handle this. Okay. So one way to ensure that would be to ensure that all these degrees are different for each one of these AI, each one of these E, okay, where AE is non-zero, this sum is different. Okay. So one way to ensure that would be ensure that would be to choose Ri such that the sum, this collection is distinct, I mean consists of distinct elements. Okay, for all, I mean this collection is, this is collected over all E such that AE is non-zero. Maybe, sorry, I'll just rewrite this set in a, okay. So this collection of EIRI, okay, where E is chosen such that AE is not 0, because that only they will anyway come into consideration when we expand Y. Okay, those are the only terms of F. Okay, so distinct elements. Okay, so one easy way to do that would be, okay, choose Ri to be S to the I for some large integer S. For example, S is bigger than the degree of F. Remember, the degree of F is the maximum of sum of EI such that AE is 0, it's non-zero. So these are the actual terms appearing in it, and in that the degree is the largest largest term that we would get. The sum is the largest. So if you choose an S large enough, then each one of these EI will be strictly less than S, and then if you take something of the form, let's say some B1 S plus B2 S squared up to some Bn Sn, this term will be for various values. I mean, every integer which will come as in that form, if this is different from with this property, this will be different from some other B prime 1 S plus B prime 2 S square and so on. Okay, so this such a similar term. So the various these sums will be distinct elements, and hence in this sum, when we expand out this sum, precisely one of those terms will dominate, and it's why I think yeah, sorry, just one. I said Ri Ni, Rn by definition is, so here, sorry, I should. So sorry, just one clarification here. So this is sum is over 1 through n, and Rn is 1. Recall, that's how the sum will come. It's En plus Rn En minus 1 and so on. Okay. So Rn is, so just keep this in mind. And yeah, so one way to ensure this would be to choose a very large S and then choose Ri to be S to the I, and then we will get all of them to be distinct, and exactly one term in the terms of F written as Y's, exactly one term will when we do this, and therefore that would be the that would ensure that F is a monic polynomial. Okay, so without loss of generality, F is of the form y n to some large degree, some plus lower degree terms in yn. Okay, so therefore, so what do we have? We have k y1 through yn minus 1, okay, and yn. Okay, so now we may as well call, we can drop the star in the notation, we may as well call them y1 through yn. Okay, and modulo this f. Okay, this surjects onto R. Okay, f is just in the kernel, so this surjects onto R, and in this ring y is integral over the subring. So yn, image of yn is integral over the subring k little y1 through little yn minus 1 of R. Hence it suffices to prove the theorem for a smaller ring, and then we can bring it down till we actually get that there is no relation among them. Okay. So this is the proof of the general version of Noether normalization lemma, and we will prove. So remember, let's do an example, and then we'll come back to this question about finiteness and how to use it, or why is it relevant. Okay, so here's an example. So in the proof, in the first proof of Noether normalization lemma for arbitrary, for infinite field, we observe that a linear change of coordinates would work. So here's an example where linear change of coordinates won't work in the proof. So later, after we understand dimension a little bit, we will try to come up with an example where there is no, the algebraic independent elements are not even linear. So that will require some more understanding to be able to calculate something. So that we will revisit after we understand dimension a little bit better. Okay. So here we are taking a polynomial ring in two variables over a finite field of two elements. And then we look at the ideal x, y and x plus y. And so it is, and then we ask for its associated primes. It's expected, it is just, so this is the command, Macaulay command to compute associated primes. Okay. So it's as expected, because these are irreducible elements, they are all distinct primes, and if you take a product like this, it will not have any other associated primes. It requires a little bit of thinking, but in a polynomial ring one can show that. Okay, so we would like, in our proof we changed the first n minus 1 variables, and then we changed we didn't change the last variable. So we would like to change x but not y. Well, this is a finite field, and x has to go into a non-zero vector, a non-zero linear polynomial, something of the form x plus some alpha times y. Remember, that is what we did in the proof. But there is only one choice then, x. So we want to define a change of coordinates. So change of coordinates is a ring homomorphism, it's a ring automorphism. So there's only, if you want to keep y fixed, there is only one choice, and x has to go to x plus y. Okay, so this is a map from R to R. X goes to x plus y, and y goes to y fixed. Okay, and we ask what happens to I. Okay, so we are trying to find whether a linear change of coordinates of this variables x and y will give us a suitable Noether normalization for R mod I. Okay. So if you do that here, then we see that I doesn't change. This is same as that, right? X square y plus xy square. Yeah, but in the proof, if you remember, the kernel needed to have something monic in y after the change of coordinates, or the change of coordinates is effected so that we get a monic polynomial in y. But here there is only one change of coordinates that's possible, and that yields the same f, and there is not going to be any monic polynomial in this ideal, monic in y in this ideal, and so then we can't do anything. Okay? So this is an example of a case where over a finite field we are unable to find a linear change of coordinates which introduces or which gives us a monic polynomial in the kernel of that surjective ring map. Okay, so the surjective ring map, again, what I mean is R surjects onto R mod I. Okay, but just the proof that we just saw, if you instead of taking x goes to x plus y, or if you take x goes to x plus some power of y, it might work. Okay, and so let's check that. So here we change x goes to x, x plus y squared, and y is fixed. So that call that psi, and psi of r is this, and here is a monic polynomial in y. Okay, so this is what this proof does. Okay? I mean, this proof says that this is always possible. Okay? And if you think about how we constructed this polynomial, which I won't explain, but if you think about why is it that if you take this I, we are unable to get a monic polynomial, that phi of I is, there's only one phi, and phi of I is itself, or phi of the generator of I is itself, then you would be able to do this in other fields also, finite fields also. Okay, okay, so that's the proof of Noether normalization lemma. Okay, so now just yeah, so this is proceed by induction. Sorry. Okay. Yeah. So now what we want to understand is, okay. So we have so k let's say k is a field. Okay, we'll come back to algebraically closed in a little later, and R is a finite type K algebra. Okay, and this means that by Noether normalization there is some polynomial ring, some Z1 to ZD polynomial ring such that this is a finite map. Okay. In particular, it's integral. Okay. Okay. So now let's So we would like to understand. So this gives a map from spec R to spec A. Okay. In this particular case, it will also give a map from maximal spec of R to maximal spec of A, but that is a difficult theorem which we will not attempt to prove, or okay, at least in specific examples maybe we can work it out in the exercises, but in general it's not easy. I mean, that needs a proof, but it gives us a map like this. And so we continue our discussion about integral extensions and finite maps, which will prove that fibers of such a map are finite. They are so this is so if you think of if K is algebraically closed, then we can think of spec of A by its maximal ideals, and maximal ideals corresponds to point. So we can think of this as some space KD, so at least if K algebraically closed. Okay, this is okay, and this is some X. Okay, so X maps to this. This is what the picture is. Okay, the points in this one is some subset of, let's say, Kn. Okay, so some subset of Kn variety maps onto Kd. We will prove in this lecture or the next that this is actually a finite. The fibers are finite. We will prove also that this is surjective, and so then we would like to understand. So we could use this as a way of understanding X. Okay, so that we want to pursue now a little bit. So okay, morphisms, and then if you have finite or integral morphisms, what do their fibers behave? I mean, what can we say about their fibers? Okay, so that's the next topic. So before that, we need to introduce a definition. Let R be a ring. The Krull dimension named after Krull dimension of R is supremum of L such that there exists a chain P0 inside P1 inside PL of prime ideals in R. Okay. So this is what a Krull dimension is. Okay. So let's look at a couple of examples. Okay. So one of the things that we will study is how dimension behaves under integral extensions. Okay. So we need to develop a few more definitions, but let's quickly look at an example. Okay. Dimension of a field is 0. Okay. This is K field because there is only one prime, the maximal ideal, which is 0, and hence it is 0. Okay. Dimension of Z. So the only to start with, the only sort of rings that we know are Z, Q, and maybe fields that at least we know exist. Okay. At least, and dimension we have to start counting from. I mean, if you want to build up something, we have to, for an algebra, we have to start measuring it from somewhere. Okay. So now, what about dimension of Z? So there are only two kinds of primes. Only two kinds, prime ideals, sorry, not primes, kinds of prime ideals. 0 or the ideal generated by P a prime number, and these are also maximal. Maximal ideals are exactly this, and hence, therefore, dimension of Z is 1. So a Krull dimension is just written dimension, and now there will be a little confusion. Often we will have to look at K algebras, and we will have to use the word dimension to mean its vector space dimension or Krull dimension. So in that case, I will try to be consistent with the following usage, where for vector space dimension I will call rank, and dimension would mean Krull dimension. Okay. In any case, if there is a confusion, I will clarify. Okay. So dimension of Z is 1. So which means, this is always a chain, and you cannot do anything better. I mean, you cannot insert more elements here or in the middle. Okay. So you cannot extend it any further. Okay. So similarly, dimension of R equals 1 for every PID. Okay. Same argument. Maximal ideals are generated by irreducibles, and the only prime ideals are either maximal or the 0, so any chain will look like this. Okay. So this is one definition. I mean one example, and another. So just a half example. The other half is what we will struggle quite a bit to prove. So we will. If K is a field, then dimension of K adjoint x1 through xn is at least n. Okay. The reason is the following, that 0 properly inside x1, properly inside x1, x2, the ideal generated by all the variables, this has length n. Okay, so this is a chain of primes. Okay, and there is no immediate way that one can insert things in between or extend anything to that. This is already a maximal ideal, so you cannot add anything here. You cannot add anything to the left. This is already 0. and these have, so these are not, I mean, in between this, there's no, one cannot insert anything. But remember, the definition is of dimension is supremum of such chains. So we will work a little bit to prove that dimension of this is equal to n, okay, but that requires some work, that there is no some other chain of primes that will go into some other maximal ideal with greater length. Okay. And so one of the there is some difficulty. I mean, we will face some difficulty in proving it, partly because we don't actually know the structure of spec. We don't yet know the structure of spectrum of this ring. Okay. So that's the thing. So this is the end of this lecture. In the next lecture, we will start discussing further properties of integral extensions, and then we will slowly, so then we will have to spend time understanding Krull dimension more properly, and that's what we will do.